Kazimierz Rzążewski, who agreed on a very short notice to save the day. Andrzej Krasiński called me 48 hours before this seminar that he became ill, and of course that was a disaster, but here we have a very good substitute, if I may say. Okay, thank you. Yeah, that's a last minute call. Fortunately, I had the talk prepared because last Thursday I gave almost the same thing in Barcelona at the meeting for the anniversary of two our friends, Maciek Lewenstein, who turned 60 this year, and Roy Glauber, famous Roy Glauber, who turned 90. It was really a very prestigious meeting, and in the end, I think, Klaus Zengstock from Hamburg now. This guy is younger, I don't know him. Luis Santos from...
Hauke.
Yeah, Hauke, that's right. Luis Santos from Hanover, Peter Zoller from Innsbruck, Pierre Meistre from Tucson, Dan Klepner from MIT, Pierre Meistre from, I'm sorry, Alain Aspect from Physical Regulators. Yeah, Alain Aspect from Orsay, Pierre Meistre from Tucson, another Nobel Prize winner, Bill Phillips, and there is another guy here. Charles Clark, probably many of you remember, our friend Tilman Pfau, of course Fritz Hacke, and many others. Sandro Stingari, a lot of colleagues. So that was really very nice occasion. I was asked to be one of the speakers just because our connection, of course, to Maciek, who really grew up in this institute, some years ago, of course. So, advised by Professor Białnicki, I started off by showing a picture of Maciek getting the prize of the Foundation for Polish Science in 2011. Then I also said that Roy also got some prizes, and that's the one that he's getting, slightly, a bit more Polish. Yeah, that one is sometimes called Polish Nobel. Right. And at this point, let me turn to the talk, really. I will tell you a little more than I had time to say in Barcelona. I will tell you about dipolar dark solitons. It's a paper that has appeared just last Friday in the Journal of Physics, written together with Krzysztof Pawłowski. Pawłowski is not here because his child got sick and he's caring for the child.
But he is also attending to this.
Yes, but he was typically coming on Wednesdays. And just this morning he told me he can't. Okay, so it will be about solitons. Everyone knows, probably solitons are these non-spreading solitary wave packets that propagate in the media without distortion. And these are very special media, not just any, but very special, for which spreading, which is typically caused by the dispersion, is somehow counterbalanced by the nonlinearity of the equation describing the wave. In strict mathematical sense, as probably most of you know, not every situation where some well-defined wave packet can spread without much distortion really deserves the name of a soliton. There is a special class of equations that admit not only single but also multi-soliton solutions, and those special equations also have this property that solitons collide, so to say, without distortions, go through each other only with some kind of a phase shift typically. Apart from some classic, you know, these waves in the, yes, with the channels and so on, closer to modern physics, there were, rather long time ago, there were examples of optical solitons, that light pulses in some special situations could travel without such distortions. And something that I grew knowing about and is now forgotten is something that was discovered by McCall and Hahn in the 60s of last century, and these are so-called self-induced transparency solitons, namely the non-spreading wave packets that travel through the medium of atoms for which this carrier frequency of the light is the exact resonant frequency. And then there is some condition under which each atom is going through absorption and emission, making for the solitonic wave. Much more important and actually very modern and even, I would say, telecommunically relevant solitons, optical solitons, are in the Kerr nonlinear medium. This is really well known and studied a lot. Okay, so these are some most famous examples of the equations that admit multi-soliton solutions. These are some perfect situations. Typically, x goes from minus to plus infinity, so it's a full line. Of particular importance for us, for this talk, at least temporarily, will be this so-called nonlinear Schrödinger equation, where there is this nonlinearity here. Optical solitons are of this kind because Kerr nonlinearity leads to the cubic term in the evolution equation. Okay, so this nonlinear Schrödinger equation, those people who work on Bose-Einstein condensation, of course, link immediately to the Gross-Pitarski equation, which looks exactly the same. So very early, people started thinking about solitonic waves, matter waves, in BEC. On the full line, it is of soliton category. However, there are many imperfections that from time to time become of importance. The first one is not very severe, but worth remembering, namely that unlike typically for the Kerr medium, this coefficient G here for the standard BC is positive. For those positive G's, we like to say repulsive interaction here, solitons are dark. In other words, they are dips in the otherwise finite density profile of the condensate. So these are dark solitons. Of course, in reality, we never deal with an infinite line, that's obvious. That is also a little bit of a complication. Always practical systems, to some extent, are 3D, and these transverse directions are somehow of some importance. Almost all experiments with BEC are not done not only on the infinite line, but not even on the finite line, because there is additional binding harmonic potential, bending like this, that is of course not present in the nonlinear Schrödinger equation. And yet, very early, around the year 2000, in two different places, at NIST, in the Bill Phillips group, and in Hanover, in the group of, the big boss is Wolfgang Erdmer, but Klaus Zengstock was the guy who was really implementing this. People thought about engineering a soliton, dark one, on the BC, and for this, to this end, they wanted to create a phase, x-dependent phase with some kind of a jump, because such a phase jump is characteristic of the dark soliton. To do this, they have discovered incredibly simple method. Imagine that this is the condensate. Imagine that this is some kind of the partially blocking little plate. Actually, in the experiment at Hanover, it was a razor blade. And then we shine light, and this light is really affecting only half of the cloud here. Now, if the light is strong, then indeed the resulting is the phase shift of the wave function, which is x-dependent. It's different here than here. So, this is the phase shift. This is again this phase imprinting method, and the resulting is a little dip, or deep dip in the condensate, and which under some circumstances travels. If the jump is full pi, then it is really dark soliton touching zero here. Now this is one of the first experiments. Experiments were done almost simultaneously in Hanover and in Gettysburg. This is the soliton which travels downwards, and these are the theoretical predictions for the same parameters. And there is a lot of friends and also a lot of people that were in Barcelona here. Of course, Maciek was on this phase paper with his wife Anna Sanfera and also Żola Szlapnikow working on the theory. Zemstok I was showing on the picture. Wolfgang was also in Barcelona. And of course, also at least, obviously Bill Phillips, whose name is somewhere here. Bill Phillips was the big boss. But the theory was done under supervision of Charles Clark, another friend of ours. So that was a good picture to show there, yes, in Castel de Fels, because 1/3 of the authors were in the audience. Now, things went on, and in 2008, after writing several other papers, Klaus Zemstok, who in the meantime got a position in Hamburg, really perfected experiments with the solitons, and this is the first beautiful observation of the solitons interacting, colliding, yes? Colliding without distortion, that's what happens here. The period of oscillation is approximately well known. It's about √2 times the period of this harmonic binding potential. That was tested here. The fact that there is practically no distortion was also revealed. I want to say that to produce such a picture, it's not possible just to trace the single copy of the system, because each of these pair of points comes from the destructive imaging method. So by holding everything for slightly longer time and distracting it, they are getting for different runs these different sets of points, and that's how they are able to trace the evolution. A year later, in 2009, another friend of ours, Wojtek Żurek from Los Alamos, conjectured that solitons, to have solitons in BEC, one does not really need this phase imprinting method. He said, if I imagine quasi-1D gas and cool it very, very rapidly, then conditions for condensation are reached independently in various segments of this little nearly line. Hence, locally, the phase of the wave function will be fixed. However, if it is really so rapid, then the highest speed of information crossing here, which is the speed of sound, is not sufficient to really make phase, local phase here, known or available to the nearby places. Thus, he says, fragments will be condensed, each with its own phase, and when they merge at the intersection, there will be a phase jump. Hence, there should be dark solitons created automatically by a rapid cooling process. And then we did the numerical experiment on this. We started off with the trap like this, putting gas above critical temperature inside, and then we lowered the shoulders, letting fast guys out, So the condensate was created, and then we closed the trap to really go to the standard harmonic oscillator by binding to see the evolution. And the evolution you can see in many places, including this institute 2 flights down. Very short coherence length at the beginning, very funny, complicated structure. And then, as we cool off, as we lose a lot of atoms, then clearly traces of solitonic waves are emerging. So Wojtek was right, we checked, and I don't want to go into these details, we checked some statistics of this solitons and compared it to his theory. It did not work very well, but I don't want to.
Excuse me, can I ask a question?
Sure.
Does it matter what the size of the discontinuity phase is? Does it have to be?
Yes. No, it does not have to be pi. If it is less than pi, then this is really gray soliton, not dark soliton. Okay? So the minimum is not 0. Yeah. Well, this is the later part of the previous picture, and you can see them even clearer here. And this is my favorite picture, which went to the cover of PRL. These are these phase domains, yes? And you see clearly these phase jumps. All these pictures that I'm showing were really made by Piotr Dewar. So he is really the artist behind.
The phase is discontinuous?
Yes. Yes, well, of course it is sharp.
Yeah, but it cannot be discontinuous because the function would not be differentiable.
That's right, so there is some kind of the shape, yeah, of course. After all, this is numerical calculation, so even the answering whether it is discontinuous or not is not possible, yes? Okay, now, as a next step, in another PRL, we noticed something to us even more surprising. We noticed that really this rapid cooling that Jurek advocated is not necessary. That actually one can get these solitons, find these solitons even in a thermal state, in the thermal equilibrium gas. They just are spontaneous. And this is the situation not in a trap, it's situation in the box with periodic boundary conditions, for the reason that I will explain just in a second. And you see very clearly the slow moving lines, and they are of course solitons. There are also fast moving lines, something which travels practically with the speed of sound, and these are phonons here. So there are both phonons and solitons in such a gas, and we did nothing, we just started with the thermal equilibrium. I sweep under the rug,
But is this?
how do we describe thermal equilibrium gas? I won't talk about it.
Is this surprising? Because nonlinear Schrödinger equation is completely integrable. So we know that there are these two sectors, soliton sector and the wave sector, the phonons as you call them, and the solitons. And any initial conditions should, if you are lucky, split into the two, into
Yeah.
this.
Of course, I like this
So-
remark, yes. And I share this view, yes. But believe me, this is really very surprising for the experiment.
Yeah, I'm not saying it, but I mean.
Okay,
it's mathematics.
so the next stage is something very nice, very interesting, and quite sophisticated. Namely, back in 1963, Iliot-Lip and Liniger, they have solved exactly a multi-particle model for atoms sitting on the circumference of the circle with these contact interactions, very much assumption that is always made when deriving the Gross-Pitaevsky equation. And then, almost ever since excitations of this model in this exact solution were described and computed by Lee, people started discussing it. Namely, this interesting multi-particle equation has two branches of quasi-particles. One branch is kind of standard by then in 63, experts knew about it. That's so-called Bogolubov spectrum, consisting of phonons and then a quadratic curve describing what people call particle excitations here. But there's another branch, second type excitations. Lieb had no idea what is this meaning, what's the meaning of this thing. And it was Ludwig Faddeev who was the first to notice that this curve here is identical to the dispersion curve for solitons of nonlinear Schrödinger equation. And then he said, okay, so there is some link between these guys and solitons. Okay, then many others were making this claim, bringing different arguments. I mentioned, well, there was some Japanese paper, there was this guy, very influential guy, Lincoln Carr, who claimed also that he really proved without the slightest doubt, that quasi-particles of the second kind from Lieb linear model are what are the solitons in the nonlinear
This is a linear
equation.
theory.
I'm sorry?
This is a linear.
But many body.
But
Yeah, but the equation is
Gross-Petersky equation
Mean
is
field.
also a mean field approach to the many-body problem. So that's even nicer, yes? Well, the claim is nice. The question is what sort of strength the proof has. And in my opinion, everything that was developing in this area was kind of doubtful. We had our own little contribution to the discussion, published only this spring, where we looked at the statistics. We just assumed a thermal canonical distribution, a thermal state of the quasi-particles from the Lieb model, and then looked at the temperature dependence of statistics of our solitons in our simulations of the thermal gas. And we found a very nice agreement. I don't want to go very much into detail. Here is momentum, here is a number of solitons. For very low temperature, I don't remember which curve is which, there is a very nice agreement. When temperature gets higher, still these are pairs of curves which are quite close, not exactly the same. However, I want to stress that first, in these higher temperatures, Lieb linear is not enough. One has to go to the so-called Young and Young extension of the Lieb model that is correct for higher temperatures. Also, there is some collection due to collisions, even though these collisions look like completely elastic, there is this phase shift, and then we had to account for this by having one adjustable parameter for these three guys. For this one not, at low temperature. There are so few of them that collisions do not play much role. Okay? Now I want to stress that it was Krzysztof Sacha in a recent paper, for which last night I could not find the reference at home, who really, in my opinion, put the final, final argument linking these guys. You see, there is a puzzle here. If you imagine this completely uniform circumference, yes, this circle, and atoms there, of course Hamiltonian there is translationally or rotationally, depending on your geometry, invariant, then you should understand that out of this one can get very easily that every eigenstate of this Hamiltonian, when reduced to the simple particle density, must be completely uniform. There cannot be any dip. If dip, then where? So, and yet, of course, in this multi-particle description, there is a dip, and we are talking about this dip all the time. And Krzysiek had a very good idea. He observed that what corresponds to the solution of the mean field equation is actually not a single particle distribution from the multi-particle Schrödinger equation, but rather the whole many-body probability distribution, if you really take the multi-particle wave function and draw points for particle positions according to this multi-particle probability distribution, then in fact you find these dips, and they agree very nicely in terms of the shape and so on with the soliton from the nonlinear Schrödinger
But
equation.
that just means that this state is highly degenerate, that the dip can be anywhere.
No. No. I have only one eigenstate. But this eigenstate, of course, is described by a multi-particle wave function. I square it, then I get a complicated multi-particle probability landscape.
Yes.
And now I draw particle positions one by one according to this. And that will have a dip. So it's a single eigenstate which, viewed correctly, viewed from the point of multi-particle.
But where is the dip?
Oh, it depends. It's random. It's a question of probability.
Okay.
It can be here or here. Of course, in other words, if you repeat this drawing, then it will be in different place, of course.
Okay.
Yes.
Most
So-
probably.
It will be most probably in different place. Okay. I like it so much, and I really feel ashamed that I did not have this idea before. Okay. In this paper, we also looked at the thermal solitons in the harmonic oscillator, and also with the transverse, some little finite width of the sample. We even chose very realistic parameters, and Przemek Bienias made this calculation, and we indeed see very similar thermal solitons. Now, the introduction is over, and the remaining minutes I will spend telling you about this newest paper. Well, we know dipole-dipole interaction between fully polarized gas would be given by such a formula if Z is the direction of the dipoles, and the specific thing here is that whether it is repulsion, first of all, it's of course action at the distance. Second, whether it's repulsion of attraction depends on the position of this, relative position of these atoms. In this case, we have repulsion. In this case, we have attraction. And that is, of course, bringing a lot of new aspects to the problem of condensate. So, in 3D full equation, kind of generalized Gross-Pitarski equation would be like this, with this integral thing, with a kernel given by this dipolar potential. Simplification that we will make is to take this wave function in the form of a product of ground state in the perpendicular directions, those directions of a very strong squeezing, and what we will derive then would be the reduced equation for the Z-dependent function with another effective potential which has to be computed. It's been computed by several authors before us, and so we could just check it in the papers. Okay, so what happens is we are taking now quasi-one-dimensional gas, long, capital L is the length of this in this direction, and we take perpendicularly harmonic confinement, and most important parameter here is the aspect ratio. So the ratio of this size of the wave function in this direction compared to the length L, capital L. So that's important thing. As I say, we've got polarization which is perpendicular to the long axis, so dipoles, at least dipoles which are quite far away, certainly repel each other. Here is how this intersliced potential looks. It has 1 over z to the 3rd power tail, as expected probably, and very rapid fall for very low distance. And this rapid form has its characteristic width, and not unexpectedly, width of this part is of course about the size of the wave function in the perpendicular direction. Why? Well, because when atoms get very close, about as close as this is the width, then some attraction pops in, and that is changing the character of the interaction. Something which is kind of nice is that it attains a finite value at zero distance, even though original 3D potential is of course singular. There is some trace of singularity here, because not only we get this potential, but we also get the delta function or the contact term in the equation. Now, there are many other reasons for contact term, in particular van der Waals forces. They can be checked and modified by so-called Feshbach resonance method. So just to really study the effect of this long distance interaction here for the solitons to be, we assume that contact term was killed by the Feshbach resonance method. So this is the only this effective potential that we detect. Okay. Now we are on a finite size interval with periodic boundary conditions. So then the question is, how do we engineer, imagine now this phase imprinting method, how do we engineer, say, pi or some other phase shift? If we do this, then this will not match on the other side. So the trick to do it is to assume that the phase has also a linear part, and that it jumps, but then also smoothly links to be joined on the other side at the end. And these are the solitons that we are getting this way. This fuzzy line is the Zaharov and Shabbat soliton, so it's a soliton exactly from the nonlinear Schrödinger equation with negative g. If lambda, this, you remember, this aspect ratio, is 10 to minus 3, our soliton is, well, according to this picture, indistinguishable. It's almost the same. At 10 to minus 2, it develops shoulders, and at this highly exaggerated, that's not really one-dimensional situation, 10 to minus 1, this is really looking different than the reference Zaharov-Shabbat soliton. Whether it is stable, well, let's create such a guy for lambda equal 10 to minus 2 and propagate, and you see it stays like this. One has to remember, of course, that we are plotting this in a co-moving frame, because the fact that we have engineered this smooth face going around means that in this case our dark soliton is traveling, is not standing still. Okay, now so much for single soliton. This is very, I don't remember what are the units here, but this is huge, very long time, so it's really incredibly stable. There are certainly, in the experiment, there will be certainly 5 or 6 other reasons to destroy everything before such a long time.
Excuse me, does this mean that the velocity is quantized in this?
No, it is not. No. Well, it is well defined by my pi shift at 0, plus the length of the...
Okay, because you can vary the shift at 0.
Quantized in the same way as distances are quantized here. Okay, so the next stage is, of course, a pair of solitons, which is much more interesting. So Krzyszek engineered this pair of solitons. Now with pair, there is no trick with this linear thing necessary, because it goes pi 0, and then back to pi, and then it fits. Yeah? So he started with various initial positions and looked at acceleration, because as it turns out, our solitons, unlike original nonlinear Schrödinger equation solitons, do interact. Out of this acceleration, he made numerical integration and got a potential curve. And this is a potential curve this is a distance between solitons, and the potential curve is like this. There is a very steep repulsive almost wall. There is, as you can again guess, 1 over z cubed tail here, which is attractive, and then there is clearly a very nice minimum here. Okay, now the question is, are collisions elastic? So let's start with the initial state A, which is above this, so to say, ionization barrier. What you expect is what you get, namely these guys go through each other. Because of the periodicity, of course, they reappear and collide again, and not much is happening. It looks really like a elastic collision. What happens if we start with B, deep here? Of course, again, just as picture indicates, we've got a bound state and these guys come close and repel and then attract, repel. If we looked closer at the period here, then we could maybe detect something. However, something really nice and dramatic happens if we start off here, somewhere far away, very close to this, as I call it, ionization threshold. What happens is that really the collision is inelastic, and after a couple of bounces, they really go away, depart, and then resume something which is like here. In other words, from the point of view of this picture, they gain energy. Yes, they gain energy while colliding. To look closer into this, how much time do I have?
They will have 20 minutes.
Wow. No problem. To look closer into this, all these calculations are for lambda equal -2, which is not bad.
So there is some phase transition between the two regimes. At
No.
some point.
Just wait. Well, phase transition, it's like having ionization process. Of course, there is a threshold. But. I go back to my sentence, which I did not finish. To look closer into this non-elasticity here, we exaggerated a little bit. We went to lambda equal -1 to have our solitons even more distorted compared to the Zakharov and Shabbat solitons, and we looked at such a collision. And in this case, this one collision is already bringing us above the ionization threshold, and these guys go around. However, look closer. What happens in this region is creation of these fast-moving guys, so there are phonons produced. Yes? So collision is inelastic, and phonons are being produced here. These phonons, of course, go around, so they reappear here because we have a finite size sample with periodic boundary condition. A red line is the velocity of sound, showing the velocity of sound with this gas, and you see that they travel more or less with the velocity of sound. So it is very much like radiation of accelerated charged particles, except that we are used to the fact that such a particle, when radiates, would rather slow down than speed up. Why these guys are speeding up? Well, because dark solitons can be viewed as something having negative mass. And just because of that, radiation speeds them up. However, radiating and actually decreasing energy, going faster, thus decreasing energy, make them slightly shallower. This is, of course, not visible on this picture. However, one can trace this. One can trace the depth of the soliton as they collide. So, Krzysiek did, and here is a very nice picture which I like very much, and which also, I think, sells very well in the quantum optics environment. So, what we have here is a couple of thousand of collisions, very, very, very long time evolution. And this is the depth of it. So, in other words, graying is shown here, yes? So the first part is some kind of a linear, that's the, I would call it spontaneous emission. But then, since our phonons do not escape here, they come back, there is also stimulated emission. These guys help to produce more phonons. Avalanche is appearing, so I would call it like a super radiant phase of the evolution. However, these guys do not escape to infinity. They are around, and at some point there are so many of them that processes of absorption and emission equilibrate. And some kind of equilibrium is reached, which is kind of nice. There is some quasi-temperature which appears here between these phonons and these two solitons. I can tell you that even here, I don't have this picture here, our two solitons are still clearly visible. Clearly visible. Again, quantum optics audience, and having Roy here and Fritz Hacker there, I could also stress that there is some analogy between these enhanced fluctuations here and what these two famous guys did for superfluorescence pulses, finding the statistics of energies of these pulses. So there is some analogy. You know, in the thermal equilibrium, there is a lot of...
This is not the Boltzmann distribution.
No. Oh, this is some kind of the field with a hyperbolic secant square or something. You know, something taken from this, something taken from the semi-classical picture of the spontaneous emission, which actually coincides with this initial phase of superfluorescence again in the Fritz and Roy paper. It's for maniacs. Okay, so our next and last for this paper question was whether these funny dipolar dark solitons also appear in thermal equilibrium. For that, we had to engineer some kind of the construction of the thermal ensemble, and I don't think I want to go into detail. In this case, we started off with a Bogoliubov energies, and then we distributed Bogoliubov energies according to the canonical distribution. It was not a very good thermal state, but then we would evolve it for some rather long time, and then we would say, okay, nothing, there are fluctuations, but nothing, there is no trend, nothing really changes in some monotonic way. So this is a good example of the thermal equilibrium. And then we looked at the evolution, indeed finding solitons. And then we looked again at the statistics of the solitons as temperature is changing, and temperature is not such a good parameter. We do not have a good, so to say, thermometer here, because as I said, we put some temperature here, but at the end, after some evolution, this is slightly different temperature. We don't know exactly what is it. But what we know is how much condensate is in the gas, because condensate is just the zero momentum component here in the decomposition of the wave function. And this is just a picture very similar to the one we had for the contact interaction. There are some solitons around, and here is statistical distribution for, you could say, for temperature. Temperature higher is here, temperature lower is here. This is a histogram, and these green points are for the corresponding calculation for the Gross-Pitaevsky equation with contact interaction. Of course, they are not identical, but there is close similarity. What it means? Well, it means that maybe we were slightly too fast saying that statistical aspects, statistical features of the contact interaction, thermal, spontaneous solitons, coinciding with those for Lie, are some kind of a indirect but proof of a link between these two things. It's a higher side. Because we are pretty sure that these calculations are not in some direct correspondence to Herpendick model. These are long distance interactions, we just on purpose we killed the contact term, and the size of this interaction really matters, as I was showing here. There are these interactions between distant solitons, and there is this graying, there is this interaction with phonons, and so forth. So I would say that what I've been showing towards the end, it would be too strong to say that it contradicts some of my claims 10 minutes or 20 minutes before, but at least they open some question that we would, of course, would like to answer, and perhaps we will try to answer in the near future. As a last point, I think. Thank you.
But thermodynamics in this case is not really applicable to full extent because this system is not in equilibrium, and there's too much coherence, I would say, in it to apply, or too little randomness.
There's a lot of randomness. Positions of these solitons are completely random.
Yes,
All
but
of them are completely
during the process there is this coherence here that persists over the whole system.
Yes, and this is why. Yes, and this is really the origin of something that we were discussing 20 years ago with Mariusz a lot, namely that this sort of problems are not in the class of problems for which there is the universality of ensembles. This I agree.
This goes back to the idea.
It goes back to the fourth. Yes, also to the problem of difference between canonical versus microcanonical and so on. I agree. This is really related to the persistent coherences. In other words, it's related to the presence of the condensate, because this is where the coherence is. Yes, Mariusz will give you.
Yeah, no, I want to comment the Professor Tusk's comment from the very beginning. He was very clever to note that it is obvious that there are solitons,
Yes.
because, and I want to say that this is why it is not obvious. On the one hand, you have many-body Schrödinger equation, which
This
is
is another
linear
story.
and has two kinds of excitations. Nobody saw any solitons. This was only a belief that the second branch of excitation are solitons, due to idea that they have similar excitation spectrum, but nobody was able to take n-body solution and show, look, this is soliton. It didn't look like soliton. So on the other hand, this is mean field equation, which is single particle equation, which is nonlinear. And people knew that there is only Bogoliubov spectrum, and they made a lot of predictions about the features of 1D system based on the Bogoliubov spectrum.
Yes.
So the standard point of view on condensate on a line in 1D was that there is this quasi-condensate where there are many of excitations, but only of Bogoliubov type, which gives the coherence length to be smaller than the size of the system, and at lower temperature there is a condensate. And out of a sudden, it came that this is very close link between many-body solution and this Gross-Pitajewski trivial equation, that this Gross-Pitajewski equation has also these two kinds of solutions, but one has to look at finite temperature, not at zero temperature. So
Yes.
it's very, very unexpected and changed totally the point of view on 1D system.
Łukasz does not need any defense, but what you
historically
have said
it was
is of course correct, but it's not really contradicting what
No.
he has said.
No, I said that he was very clever to know
Yes.
it at the very beginning, but I wanted to say that it was not trivial to see it.
Well, the reason, I mean, I understand that this is a many-body case, but there are other many-body physics cases where it's a very similar situation that happens. Namely, if you look at the magnetic systems, magnetic chains and the chains, there is a many-body solution if you look for what happens to the individual spins. And then you have this kind of a condensate, and you have all over the sudden, out of these single spin excitations, which are very complicated and so forth, you build up solitons and photons and so forth and so forth and so forth. The one thing which I probably is hidden somewhere there, and we can, if you have it only a Schrödinger equation, in addition to this what you call phonons and solitons, there is a third kind of excitations, Knoyler waves.
What?
Knoyler waves. The kind of a harmonic waves of definite amplitude.
Yes.
And they have this tendency of disintegrating into a solitons because they are unstable. There is a kind of instability of this solution. Is something like this also happening in this model? I mean,
Probably in some transients, if we look closer into some cross sections, there could be also something like this. But on the long,
that
you know,
presentation, it's impossible.
in the long time evolution, there is, we do not see that.
Because they are unstable.
That's right. Yes, yes. But in the thermal equilibrium, one has to point out that solitons are being born and destroyed, with some kind of a statistical equilibrium statistics, yes, which have computed, and they are awaiting some confirmation, like experiment.
But this fact that they are created and destroyed in the substatistic is characteristic of this many-body system, which are like the magnetic systems where also those solitons are being created, and the gas of solitons are observed, particularly also in Hanover. Hans Wiekeska and the other guys.
One question. So, is it possible, if the energy of the soliton goes down sufficiently low levels, is it possible that it attains the speed of sound in the medium?
Yes, when it disappears with the speed of sound. In other words, when velocity goes, when velocity goes to sound, the depth goes to zero. So in the limit, they merge with photons, yes.
If there are no more questions, we thank you again.